Howdy, howdy. This is Mr. Potter. In our last episode, we talked about how to estimate the area under the curve by using rectangles. And we had three main techniques that we were using. The idea was that we could use the left endpoint or the right endpoint to determine the height of our rectangle, or we could use the midpoint of our interval to determine the height of our rectangle. And so I want to do a real quick recap with the example that we were doing yesterday. Yesterday we had our function y equals the square root of 9 minus x squared, and we were looking at it on the domain from 0 to 3. So for what we were doing, we graphed our function, and of course it ends up being the top right quarter of a circle when I graph it from 0 to 3. And so when I'm doing a left-hand Riemann sum, I'm using the left endpoints to determine. So my function at 0, my function at 1, and my function at 2 determine the heights of my three rectangles. So I've got a rectangle here, a rectangle here, and a rectangle here. And each of these has a base of 1. In fact, I could actually say that my delta x here is 1. And so what I'm doing is, because I'm doing base times height, I'm doing the square root of 9 times 1 plus the square root of 8 times 1 plus the square root of 5 times 1. And so we notice that this ended up being our left-hand Riemann sum. So for our purposes, that's approximately 8.065. And if I wanted to evaluate my right-hand Riemann sum, that means I'm going to be using the right-hand endpoints for each of these intervals. In other words, my function defined at 1, my function defined at 2, and my function defined at 3. And when I draw these rectangles, I notice some repetition here. I notice that this red rectangle that I'm graphing is exactly the same as this brown rectangle that I had. And this red rectangle is exactly the same as this brown rectangle that I had. The only rectangles that aren't the same are the endpoints. The left Riemann sum uses the leftmost endpoint, my function at 0, whereas my right Riemann sum is going to use my rightmost endpoint, where my function is 3. In other words, the height of this rectangle is 0. And so again, because delta x in my case is 1, I'm doing my right Riemann sum I'm going to be looking at my right endpoints, which were radical 8, radical 5, and square root of 0. And I'm going to be multiplying each of these by 1 and adding them together. And I notice that my right Riemann sum is equal to 5.065. And we also talked about how Riemann sums could be overestimates or underestimates depending on our function here. Obviously, my left Riemann sum is an overestimate because there's extra area here that's being included that isn't part of my function. And my right-hand Riemann sum is an underestimate because I'm ignoring area that should be part of my function. And so a good question here is, what if we were to split the difference? In other words, what if instead of looking at these as rectangles, if I was to look at this as trying to find the area of this trapezoid. Now, this trapezoid's really standing on its side, so for the purposes of my trapezoid, this is base 1, this is base 2, and this distance here is my height. So we have what we call trapezoidal approximations. So we're going to do an example here with the same function we were just dealing with. So I'm going to graph my function. It's the same function, y equals the square root of 9 minus x squared. I'm still doing it on the domain from 0 to 3. But when I graph this function, which is the top corner of a circle, on my domain, instead of looking at rectangles, I am still going to look at my function at f of 0, f of 1, f of 2, and f of 3. But I'm going to think of these in terms of trapezoids. So I'm going to have a trapezoid here. That's a horrible line. I'm going to have a trapezoid here. And I'm going to have a, let's call it a degenerate trapezoid here. A trapezoid where one of the bases is 0. Remember, this is the square root of 9, this is the square root of 8, and this is the square root of 5. So these are my lower bases of each of my trapezoids. And the square root of 8, square root of 5, and 0 are the upper bases of my trapezoid. So for this first trapezoid here, I'm going to have 1/2 base 1 plus base 2 times my height, and my height is the distance here, which is what we call the base. It's 1. Over here, this trapezoid is going to be 1/2 times the square root of 8 plus the square root of 5 times my height of 1. And this trapezoid here, even though it's really a triangle, it's going to be 1/2 my lower base plus my upper base times the height of 1. And so this trapezoidal approximation is really 1/2 times 1 times the square root of 9 plus the square root of 8, which is this one, plus this one, the square root of 8 plus the square root of 5, plus this one, the square root of 5 plus 0. And there's two ways that I want to take a look at this. One way I can take a look at my trapezoidal approximation is that every one of these functions, because this is really f of 0, this is really f of 1, this is really f of 2, and this is really f of 3. But each of my functions evaluated at the boundary points are repeated, with the exception of my left endpoint and my right endpoint. These are only singletons, whereas every other term in this trapezoidal sum is repeated. So that's one thing I wanted to bring to your attention. But another thing I wanted to bring to your attention is that when I look at these terms here, that's f of 0, f of 1, and f of 2. That really is my left-hand Riemann sum. And these terms here, this radical 8, radical 5, and 0, these are really my right-hand sum. So what I'm really doing here is that my trapezoidal approximation is really equal to my left Riemann sum plus my right Riemann sum. All divided by 2. In other words, this is the average of those two values that we just found on the previous slide. In other words, it's the average of 8.065 and 5.065. So if I take 8.065 and add it to 5.065 and divide by 2, I end up with 6.665. And this ends up being my trapezoidal approximation. And notice that when I'm dealing with these trapezoids, I don't nearly have as much overestimate or underestimate for each of these. What's happening is the only thing I've got is I've got this little sliver that's being ignored. So I know that what I'm dealing with here is an underestimate. But this is one of the best estimates that I've had so far. And indeed, what will happen is the trapezoidal approximations will always be better than the left-hand sum or the right-hand Riemann sum because it incorporates the differences in both. In other words, the errors in one are compensated in the other. And so I end up with an approximation that's a very good approximation. And this is not nearly as much work as it was trying to do the midpoint Riemann sum that we did in our previous slide. That was a lot of work because I'd have to figure out what the square root of 8.5 is, the square root of 6.25 and the square root of, I mean, that was hard work just coming up with those numbers off the top of my head. So I want to do another example of this trapezoidal approximation. So I'm going to look at y equals x cubed, and I'm going to look at it from the domain from 0 to 2. So looking at this, I've got the domain from 0 to 2, and I'm going to go ahead and do 4 rectangles here. So this is my function y equals x cubed. And I'm looking at it from 0 to 2. So there's 1, so that means this has to be 0.5, this has to be 1.5, and this has to be 2. So if I'm looking at it from my left Riemann sum, my delta x for both of these problems is going to be 0.5. So I'm going to have 0.5 times my function evaluated at the left endpoints, which should be 0 cubed, 0.5 cubed, 1 cubed, and 1.5 cubed. So it's going to be 0 cubed plus 0.5 cubed plus 1 cubed plus 1.5 cubed. So that's 0 plus, this is 0.125 plus 1 plus 3.375. And I'm taking this sum and essentially taking half of it. So this is 3.375. That makes it 3.5. That's 4.5. And 4.5 divided by 2 is 2.25. That's my left-hand Riemann sum. If I'm looking at my right Riemann sum, it's going to be 0.5 times the functions evaluated at the right endpoints of each of these domains. So at f of 0.5, f of 1, f of 1.5, and f of 2. So I'm going to have, again, 0.125 plus 1 plus 3.375 plus 2 cubed is 8. And again, notice that the only difference here is that this left-hand endpoint is being replaced with this right-hand endpoint. So I'm going to have to take half of this sum here. So again, this is 3.375 plus 3.375 plus 0.125, which is 4.5. That makes that 4.5. And when I add 8, I get 12.5. And 12.5 divided by 2 gives me 6.25. That's my right Riemann sum. And so if I want to find my trapezoidal approximation, I'm essentially going to be adding these two values together and dividing by 2. So I've got 2.25 plus 6.25. And I want to divide this by 2. So I end up with 8.5 divided by 2, which is 4.25. And of course, this approximation, since it's covering the trapezoid, I'm basically playing connect the dots here, this ends up being a really good approximation. Now, it also ends up being an overestimate, because in each one of these little curves, my straight line actually lies completely above this region. So I'm actually including area that I don't want. So this is an over approximation. And this actually brings up an interesting idea. We spoke last time about when our functions are overestimates and when our functions are underestimates. And remember that we're essentially dealing with 4 different situations. The situations where I'm increasing and concave up, up, the situation where I'm increasing and concave down, the situation where I'm decreasing and concave up, and the situation where I'm decreasing and concave down. And so what I want to do is I want to investigate to see if my left Riemann sum, my right Riemann sum, and my trapezoid, when we're dealing with overestimates versus underestimates. Now, when I look at these shapes and I'm looking at the left-hand side, my left endpoint determines the height, which means when I'm looking at these functions, I'm noticing that there's certain situations where I have an underestimate. And that happens when my function is increasing. And there's certain situations where my function has a very clear overestimate. And that's when I'm dealing with my function decreasing. So that means that it is an underestimate when I'm increasing and an overestimate when I'm decreasing. So that brings up some interesting things. Let's go ahead and compile this in a more clear format. Our function here is going to be an underestimate when my function is increasing, and an overestimate when my function is decreasing. And I'm liable to think that my right-hand Riemann sum is going to have the exact same behavior. Looking at my right endpoint determining my area, I've got situations like this. And so as long as my right endpoint is determining my height, I can see some things happening here. I can see in this situation that, again, for an increasing function, I'm an overestimate, but for a decreasing function, I'm an underestimate. So let's go ahead and put that in our table here. So what's happening here is this is the opposite of our right-hand Riemann sum. We are an overestimate when f is increasing, and we're an underestimate when f is decreasing. So we've got this left-hand sum and right-hand sum pretty well figured out. So what we need to do now is investigate our trapezoidal rule. And of course, keep in mind our trapezoid rule is going to connect our left endpoints and our right endpoints. So it's going to act like a secant line. And I noticed some interesting things happening here. I noticed that in this situation, I am an overestimate because I'm including this area that I shouldn't be including. And same thing is happening here. So in other words, when I'm concave up, I'm an overestimate. But when I'm concave down, like I am here and here, this is all area that I'm ignoring. This is all area that I'm leaving out. And so my trapezoid rule is an overestimate when we're concave up and an underestimate when we're concave down. In other words, there's a relationship between the calculus of the function, because the left-hand sum and right-hand sums deal with when our function is increasing or decreasing. That's a first derivative problem. And our trapezoid rule depends on the concavity of a function. Well, that's our second derivative's nature. So what happens is determining whether or not a function is an overestimate or an underestimate for a left-hand Riemann sum, a right Riemann sum, or a trapezoid determines solely by the behavior of the first or second derivative on that particular interval. So this gives us a good appreciation of what's going on. Now obviously there's something that I'm missing here. I'm going to leave this for a reader to figure out. But when I'm dealing with my midpoint, the idea is not so cut clear. Because for my midpoint situation, my midpoint's determined by my height, and I always end up with this situation of stuff that's being ignored versus stuff that I really need. So this really is a good question. What happens when I'm dealing with the midpoint Riemann sum? Am I always going to end up with an overestimate under certain situations? Am I not always going to end up with an overestimate under certain situations? That really is the question. But for now, I'll leave that for you to think about. This is Mr. Potter. Thank you for watching. Have a great day.